Okay, now we look at the calculus method, or basically the basic calculus method. We're not looking at the hard part. As you can see, it's short. So we just have the acceleration, which is we're using the first equation. So instead of just playing around with the stuff algebraic with the algebraic method, you can attempt the complicated one, a bit more complicated, just to prove that you know how to calculate using it. But basically, you just say the change in velocity over change in time, which is dv over dt. dv over dt just means the derivative of velocity with respect to time. Yes, so which means a is equal to dv over dt, and then you don't want to have that fraction, so you move whatever needs to be moved. You move dt to a, and then it becomes dv is equals to a dt. Therefore, we then integrate the both sides of the equation. As you can see, for the dv we have our limits, which are the initial speed and the final speed, uv. And then for the dt, our time, we have time is equal to 0 and time is equal to t. So that's our limits, 0 and t. And as you can see, the integral sign, the first or the lowest or the first limit has to be at the bottom, and then the highest limit, which is the upper bound, and the lower bound, the upper bound has to be at the top. And then we have to take the a to the other side for that, because we have that coefficient for dt. It's not related to dt, so we can't substitute those 0 and t into a, so we move it and make it the coefficient there to multiply the brackets. Then we just say t minus 0. That's the simple one. I did some shortcuts there, so you need to bear with me. It's a simple shortcut that we did, but there's a bit more calculation that needs to be done there, where you have to square something and divide. You'll see it later. So let's move on to the third and fourth equation. I think you have understood this part. The rest, you're now just clearing the brackets and then rearranging to find the equation that's intended. Okay, so here we are going to consider two equations from the graph analysis that we did, or from basic definitions that we looked at. Remember the velocity and the acceleration graphs that we're looking at, those purple, orange, what? Yes. So we found out our v is equal to change in the displacement over time, which is ds over dt. And then our acceleration is the change in velocity over time, or change in time. That's equal to dv over dt, derivative of the displacement with respect to time, and the other one, it's respect to time, which is for the derivative of the velocity. And then we equate the two, or we do some cancellation, or we substitute any of the values that we see there that are the same, which in this case is dt. So we substitute for dt and the like, and then we're supposed to end up with ads is equal to v dv, as you can see. So therefore we then integrate both sides like we're doing. So in this case we have our limits for ds is s and 0, so it starts from 0, and then we are displaced to the s, which is maybe meters in a certain direction or kilometers in a certain direction. That's our s. And then for the dv, it's the speed one, so it's from u to v, initial speed to final speed. And then we integrate that. So for the ads, it's different from the previous example where we did not have a coefficient there, but now we have to take that a and put it outside, or to the other side of the integral sign. And then for the other side of the equation, the v, now we can substitute the initial speed and the final speed into that v, because we are integrating with respect to the velocity. So as you can see in the blue section there, the one written in blue pointed with that yellow arrow, we find that we have our v is, we then say because our v, the v that we're talking about here is the one before the d, not after the d. So the one there is the power of the v, like it's raised to the power 1. V is raised to the power 1. That's why we don't see anything. It's just v dv. That's supposed to be v to the power 1 dv. So the v to the power 1, we have to add 1 to it, so it becomes v squared, or v to the power of 2. And then we have to take that squared and also divide it into v squared, so it becomes v squared divided by 2. So that's why you see 1 plus 1 again at the bottom. So what we do at the power, we also have to do it with the divisor, isn't it? And then we say v squared divided by 2 vu, like what we're doing with the integral. Now we put our v and u, and then we substitute for the v squared. We now put v squared over 2 minus u squared over 2. So that v in the brackets, it's just showing that it's average velocity, is just the velocity, right, in general. And then the v that's outside the bracket at the top there, that's the final speed. And then the u is the initial speed. I should have made them different so that you won't be confused, because there's a chance to be confused by that. And when you do that subtraction, because they have the same denominator, we just combine the denominator. That's why you see it's v squared minus v squared over 2. We just combine the denominator because they are all divided by 2. And then for the displacement side, we see that it's a multiply the s minus 0. Why we're saying s minus 0 is because we're now left with no coefficient for ds. So 1 to the power, so we have 1, but it's negligible. So we just say 1 to the power 1 plus 1 is equal to 1 squared. 1 squared is equal to 1, so there's no difference. So it's everything just to the times 1 just remains the same. And then yeah, we just simplify everything. For the divisor, which is 2, we make it half, and then we put v squared minus u in brackets just so that we differentiate. Then we take our half that side, it becomes 2as, as you can see, and then we end up with playing around with the equation, and then we get b squared is equal to u squared plus 2as, as you can see. So I hope you understood the procedure. I tried to simplify it and make you understand where all this v squared u squared over 2 is coming from, which is the same method that you see with the previous and the next example that we're going to have. I think it's only 2 equations that I decided not to use the calculus method, so you can try that on your own. Okay, now on the final equation. I think the algebra part is very easy. You're now just saying u is equals to v minus at, because you just rearranged the first equation, and then you substitute it into the second equation, and you just get, that time we got, I think it's the third equation, we got s is equal to ut plus half at squared. Now it's vt minus half at squared. Now for the last calculation, so that we end this video. Using the calculus method now, we have our initial speed, which is u, basically the same thing, it's speed, so it's ds over dt, basically with the previous example that for the equation that we also worked out using calculus. We then substitute the parts of equation 1, like what we did there. We just rearrange v minus at, we substitute where there is u, so that at the end of it all we will then end up with ds is equal to v dt minus at dt. If it was in the case of v, it will end up as u dt plus at dt, something like that, if I'm not mistaken. That's with the third equation. I think if you had to do the same thing with the third equation, it's almost the same thing. So therefore we integrate both sides like we're doing, but now we have a bit more terms to deal with on the dt side, which is different from the first example we looked at. So again, our limits, the easiest limits that we have, is different from speed now, because we're not dealing with speed, we're now dealing with time, which is from the dt, and displacement, which is the ds part. So our limits are 0 to s for ds, and then 0 to t for dt. And then for the ds part, we don't have a coefficient, so we just go straight to say s minus 0. And then for the other side of the equation, we start with the v dt part. The v dt, v and t, they are not the same, so we have to put it outside like what we did previously. So we just multiply that. We cannot substitute the time into speed. You see, it's different variables or different quantities. So we then say v times t minus 0 and the like, and then we get vt, isn't it? And then we integrate the at dt part. We then take a outside to the other side of the integral sign. Then we're left with t dt. T and t, they're the same, so we can do that squaring thing, magic thing that we always do in calculus for the integrals. So we then say t squared over 2. And then we substitute in t, we then substitute t, and then we substitute 0. So the reason why you just see t squared over 2 minus 0 is because with 0, if you say 0 squared, it will give you 0, and then divided by 2, 0 divided by 2 is still the same thing, 0. You cannot divide and get an answer there. So you just put it as 0. So that's the shortcut I did. Otherwise I would have said 0 squared over 2. T squared over 2 minus 0 squared over 2. But just because we already know that it's just going to be 0, so we just put it as 0. So don't be confused there. But we still use the same method we did with our u and our v for that fourth equation. And yeah, we then just clear our brackets, and then yeah, you know the BODMAS rule or BOMDAS rule, whatever you call it, brackets of multiplication, division, addition, and subtraction, and the like. So just use that order, and then you get your answer. S is equal to VT minus half AT squared. Okay, we have reached the conclusion now. Kinematic equation. So this is all that we're dealing with from the Newton's equations of motion. We have derived all of them. There's one missing there, but it's okay. It's just Vt minus half AT squared. The last one that we dealt with, that's the last one. But those are the four common ones. And the rest that you see down there, those are the basic things that we're looking at. The basic equations that we're looking at for distance, speed, acceleration, and all the integration stuff that we're doing. That's basic calculus. That's what we're just doing. That's basically how we understand it. But for the distance one, you'll see that it's if you integrate the velocity, you get distance. That's one thing that you might also need to know. Till we meet next time, cheers.